All right. Today we will be covering an implementation issue regarding linear and time invariant systems. So the implementation is done by the necessary tools that we have for implementing a differential equation. So we may either have a difference equation. Let me write it like this. We may have a difference equation for discrete time systems, or a differential equation for continuous time systems. We will start with the difference equations for discrete time systems because it's easier. The difference equation, we will immediately start with the examples, because difference equations, if we just generalize the difference equations from the beginning, it will be too complicated. So let's start with smaller examples. The difference equations are the equations that formulate linear and time invariant discrete time systems. What is another formulation that we have for discrete time, linear and time invariant systems? The other formulation is the impulse response, h of n. So if you have h of n, it means that you know the system, LTI system. But if you know the difference equation, you also know the LTI system. For instance, y of n, I'm writing a difference equation here, plus a times y of n minus 1 is equal to b times x of n. In fact, we did one example of this one using some numerical equations or numerical values in terms of a and b, and we found the impulse response from here. So it's possible to derive the impulse response from here. In the future, we will see, or we will develop much easier, better ways to find the impulse response from difference or differential equations. It will be a piece of cake. But right now, what we did was to recursively or iteratively solve and see what is y of n if an impulse is applied. So we apply an impulse and we iteratively solve for y of n, and that will be h of n. That's how we find impulse response for now. But the other thing that we can also do is to make an implementation using, so we are going to implement this using delay elements. And the delay element notation is this. It's a box as the input. It's a delay element. Therefore, if a signal comes in, like x of n, then the output is x of n minus 1. It's the trivial element that we have. The other trivial elementation of LTI systems is amplifier or gain factors, okay? So we are going to multiply a signal with A. A can be larger than 1, that means it's an amplification. It may be smaller than 1, it means it's a reduction, like a resistor or something. But we don't care about that, we will just operation. So using these, how can we implement this system? Now, once we derive for this simple case, you will understand the picture and you will be able to derive for the larger ones. First of all, we have to isolate y of n because that is the output. So what is y of n? It is equal to b times x of n minus a n minus 1. What is I have isolated, scaled by example. Then I have to divide all the right-hand side of the equation by c so that I have a naked, a standalone expression for y of n. And that y of n, I will start by drawing it and say that the output is this, y of n. Then at the right-hand side of the equation, what do I have? I have y of n minus 1 here. So somehow I need to obtain it. And how am I going to obtain that y of n minus 1? Using the delay element, of course. So I put a delay element from y of n, that output branch. I take a branch downwards. And as you see, the output of that delay is y of n minus 1. So I get it. And then what further things can I do? I can multiply it with minus a. It's just a number, so I use a multiplication. And this is the notation that we are going to use. Over an arrow, path arrow, we just indicate the scale. It's minus a, for example, which is the scale. So this is one of the components that I will have. And what is the other component? The other component is b times x of n, which is the input. So I take the input from one side, multiply by b. I take y of n minus 1, I generate y of n minus 1, and I add them up. And what's that summation? That summation is y of n. I can say that here what I have is y of n minus 1. All right? So this is the block diagram that we are looking for. This was the first example, and it is known as also as a first order system. This was a first order system, also known as, I will check the question, I will read it later, also known as the first order difference equation. What was the question now? Let's see. Does the delay element make the y of n to y of n minus 1? Yes, of course. X of n going into the delay element makes x of n minus 1. Therefore, y of n makes y of n minus 1. If you apply the delay element to y of n minus 1, it will make y of n minus 2. Okay, that's how we are going to extend this block diagram anyway. This is a first order system corresponding to the first order difference equation. Now, the order of the difference equation or the order of the system is determined by how many delays appear at the left-hand side of the equation, like here. This is the equation, and this part is the left-hand part of the equation. How many delays are necessary for that? That will give you the order of the difference equation. As you see, you need only one delayed version of y of n. So y's are at the left-hand side, the outputs are at the left-hand side, the inputs are at the right-hand side of the equation, and the outputs at the left-hand side require first order delay. That makes a first order system. I could have some delayed versions of the input at the right-hand side of the equation as well, like b times x of n plus c times x of n minus 1 plus d times x of n minus 2, etc. So what is the order of that system? It is still determined by the output delays, so it will still be a first order system as long as the left-hand side is y of n plus a times y of n minus 1. Okay, also known as, this thing is also known as autoregressive one systems. The autoregressive, in English terminology, would correspond to regression or regeneration or reconclusion of the output. So the output depends on a regenerated value of the output in the previous sample. Y of n also depends on y of n minus 1. Such systems, we call it autoregressive. Also denote them as AR1, autoregressive in short. AR1. 1, it means it's passed for the output requires the knowledge of the one passed. If you delay the input and add them up, like dot 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 is equal to, let's say, a times x of n plus b times x of n minus 1 plus c times x of n minus 2. Let's say that this is also an example. If the right-hand side is like this, for the right-hand side, we are going to use the term moving average systems. And this is moving average 2 or whatever. Yeah, we require 2 passed signals. So this is moving average 2, which is notated as MA2 or something like that. And if the left-hand side is autoregressive and the right-hand side is moving average, then the last example is, so at the left-hand side, we have a lot of delays equals a lot of delayed versions of the input, X, combined all together. We are going to call such systems as ARMA, which means autoregressive moving average. That's simple. Okay. Now let's see a moving average system, the simple moving average system. So we have seen only one autoregressive system for the time being. Don't be confused when you come up with y of n minus 1. You can always tap from the output and delay it. There you go, you have y of n minus 1. If you tap from the input and delay it, you will get x of n minus 1, x of n minus 2, etc. And the next example is essentially something like that. Y of n is equal to, this is pure moving average now. At the left-hand side of the equation, I don't have any y of n minus 1 or n minus 2 or whatever. B0 x of n plus B1 x of n minus 1. So this is moving average 1 filter. And how can we implement this? We have the input x of n, and we may have a tap from that and apply the delay element. What is the delay output? It's x of n minus 1. So along this branch, I have b of x, x of n minus 1. And I have to multiply it with b1, because y of n is equal to b1 times x of n minus 1 plus something. What was that plus? It is b0 times x of n itself. And I combine them, and I come up with y of n at the output. This is moving average 1 system implementation. Now from here, it's time to do an ARMA 1, or autoregressive 1 and moving average 1 implementation, which is essentially a combination of both. And over there comes the puzzle solving, or the trick that we are going to use. And the example is y of n minus, plus a y n minus 1 is equal to b0 x n plus b1 x n minus 1. So clearly this is ARMA. At the left-hand side, we have delays. At the right-hand side, we have other delays, the output delays and input delays. So how are we going to draw this? We can split the problem into 2 parts. First of all, let us say that this combination will produce an auxiliary signal. Let's give a name to that auxiliary signal, and let's call it z of n. So b0 x of n plus b1 x n minus 1 is equal to z of n. So let's do it. I will repeat just the same shape that I have drawn over there, you see on the screen. X of n goes into the system. We tap with a delay, and the delayed version is multiplied by B1, and itself is multiplied by B0. I combine them, and I generate Z of n. Okay, the output is Z of n. Now this Z of n is now the input to this larger equation, like this. Y of n plus a y of n minus 1 is equal to Z of n. So Z of n will be the input to this system. So Z of n will be the input. And let's make some cheating. I will just copy something from the above the first graph. You see that over there. It's with the input x and the output is y. Now the input will be z and the output will be y. Now I'm coming back just to make a reminder of how things work. What were we doing? We were making an output y of n because we need a times y of n minus 1. So we have a tap from here and we put a delay element. And here we have y of n minus 1. And that y of n minus 1 is multiplied by minus a. You remember that? Because y of n is equal to z of n minus a times y of n minus 1. So minus a is the scale for y of n minus 1. Let me write it in green again, in case you may want to track where y of n minus 1 is. And it is added to z of n, and the output is equal to y of n. So we have these two components. The first component that we have here is the moving average, and this component is the autoregressive parts. I made a combination of the two, and I get the total implementation of the block diagram. Now here's the trick, and that makes the lecture, essentially. We will be dealing with these kinds of things. What is the trick here? The trick here is both the moving average and the autoregressive are linear and time invariant systems themselves. It's like cascading a moving average and then autoregressive system, which are, both of them are individually linear and time invariant. And their combination is also linear and time invariant. But the combination may interchange their places due to linearity and time invariance. So that's what I will do. I will first input x of n in output of the autoregressive part will be fed into the moving average part. And you will understand why I'm doing this. Because this is the correct answer, by the way. If I ask you to draw the block diagram of this ARMA difference equation, then and you give me this plot in whole, and yeah, that's the correct answer. But I will ask, I will indicate in the question something else. I will ask you, for example, to give me the minimal implementation. Minimal implementation. What do we mean by that? There is a minimization process which can be done. It's as follows. Let us equivalently put x of n, and I'm going to draw the autoregressive part. Okay, this was the autoregressive part. We agree with that, the right-hand side part in the top figure. So from here to here I came. And I will do the opposite. From here to here, I will do the drawing for the moving average. So what is the moving average? The input is tapped with a delay downwards. And this is B0. The delayed version is multiplied by B1, and they are combined, and the output will again be y of n, because I just interchanged their places. Now this is first the autoregressive, then the moving average part of the LTI system, both of which are LTI anyway. So now what? The minimization is now possible. The minimal implementation tells me that this point, which is a delayed version of this point, I will draw the top with green. So these two green points are the same points, like trying to give you a circuit in PSpice, right? You may remember that. In Spice or PSpice, we know that they are connected with a wire, therefore they are the same signal. They correspond to the same node. They are not different. So the green point signal values are the same, which is meaning that since the red point that I have drawn is a delayed version of it, it must be the same as this red point. So these two red signals are also the same. So why am I generating two replicas of the same signal, the red signal, in other words, with a delay element from here and another delay element I use to generate another replica? These two red points are the same. Therefore, it's quite nonsense to have it like this, but instead we must, why don't we just do it like this? I use a single delay branch from top, and I get, so this is the red point, and I get the green and the red points here. And then, sorry, I go to the left-hand side from this red point and multiply it with minus a and add it to the input x of n. And I go to the right-hand side from this red point and multiply it with B1 and add the results to obtain y of n. Now, do you all agree that the last thing that I have drawn is equal to, so let's say the diagram of 3 is equal to the diagram of 2, which is also equal to the diagram of 1. 1 is the same as 2 is the same as 3. Do we all agree with that? Or is there a question that you have? If you have a question, just type it or say it now. If you don't have any questions, I will assume that you understand what we did here. The reason that we are doing it this way is to make two delay paths like neighbors come to side by side so that I can join them. And instead of two separate delays, I will use only one single delay. This is the minimal implementation. 3 is the minimal implementation. Why is it minimal? Because it uses the least number of delay elements with which we measure the complexity of the implementation. There's a question. I did not truly understand the second figure. Really. I don't know how to make it clear. You see, we have, let me put it by green. We have two system boxes here. The first box is in the dashed green at the left-hand side, and the second box is dashed blue at the right-hand side. Okay, this is, the left is, let's say, block 1, and the right-hand side is block 2. Okay, 2 blocks. And this is a block 1 is an LTI system, linear and time invariant system. It's moving average. Block 2 is also an LTI system. It's autoregressive. So I can interchange their places and the whole system does not change. What I'm saying is the input to block 1 to block 2 to the output is the same as the input to block 2 then to block 1 then to the output. Of course, if LTI, if the systems are linear and time invariant, and here the systems are linear and time invariant, so I just interchange the places of B1 and B2. First I plot B2, which is here. Do you agree that it's the same as the B2 that I draw at the top? They are the same shapes. And similarly, here I plot B1. Look at the shapes, they are the same. So the top shape is B1 and B2, and the bottom shape is B2 and B1. So this is B2, and the second one here is in the second implementation is B2, B1, excuse me. What am I saying? It's B1. All right. That's what I did. I just interchanged their places. By interchanging their places, I'm just trying to make these two distinct delay paths. On the top shape, they were separated by many things. It was at the left-hand side, leftmost side, and the other one is at the rightmost side. So by interchanging their orders, now they become side by side in two in this version. And then since they come side by side, their top signals value is the same as their bottom signal values. So to the top, from the top to the bottom, I can just use one single delay element instead of two, which is what I am referring to as a minimal implementation. I'm trying to reduce the number of delay elements. I'm trying to minimize the number of delay elements that I use. That's the whole trick. Okay. Now I will open a totally new page, and I will open or I will try to generalize this into an ARMA difference equation like this. The general representation would look like this. We have A0 y n plus A1 y n minus 1 plus A2 y n minus 2 plus dot 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 is equal to B0 x n plus B1 x n minus 1 plus B2 x n minus 2 plus dot dot dot. So it may extend to a large ARMA model with multiples of delays, with several delays like this. Now, when I isolate this portion at the left-hand side of the equation and put all the other A1 yn minus 1, A2 yn minus 2, etc. to the right-hand side of the equation, if I pass everything to the right-hand side will look like this. First, we will have a summation like this for, let's say, capital N. So it's order N, in other words, B sub K x n minus K. So with this one, I just made the B0 xn, B1 xn minus 1, B2 xn minus 2, etc. All of these, I combined these things into this summation. Okay, that's the summation. And then minus all the things that I have here as the summation I will write. Okay, I will subtract that. And that is this time k not from 0, but it will start from 1 and go up to n. Ak y n minus k. Okay? So that those are the things that I will subtract. Then I will put everything into a very large parentheses, and I will multiply everything with 1 over a0, or divide by a0, in other words, and that will be equal to y of n. You see that? This last equation is the general way of writing a difference equation, an ARMA difference equation. But this is still not very much general. It's like more like when their orders are the same. So n is equal to 3 for autoregressive and n is equal to 3 for moving average. When their orders are different, you know what that means? That means an exam question. So I'm going to do this, which is the easy case. When this n and this n are the same, n, when they are the same. But when they are different, when one of them is larger than the other one, things will change. The shape will change. What shape? First, let's draw the easy shape, and the difficult shape will be, of course, your exam question. For example, for x running index, I will give you 3. And for y running index, I will say that that top summation index will be 2 instead of 3. It will not go to the same point. So, and I will ask you to draw the minimal diagram. Or the first one is 2, the second one is 3. One of them is very difficult, by the way. It's a little bit more tricky and complicated than the other case. Because when we try to implement this, it's going to be like this. We will have the input, x of n, and the moving parts will give me the delayed version for x of n minus 1, and further delayed version will give me x of n minus 2, etc., until the last delay element, which will give me x of n minus capital N. So here I have x of n minus capital N. Okay, I have delayed capital N many times. So what is x of n multiplied with? X of n is multiplied with b0. B sub k for k is equal to 0 is b0. So we have b0 here. And then we have b1, which multiplies x of n minus 1. X of n minus 2 is scaled by b2, blah, blah, blah. The last one is scaled by b sub capital N. And here we have one before that. We have b sub n minus 1, capital N minus 1, etc. And they are all added. Like this. What does this make? This makes an auxiliary signal which could be thought of as the right-hand side of the equation totally. So you can say that the signal is z of n here. So I combined all these things and obtain, let's say, z of n or something like this. So this signal here is essentially z of n that we have. Now that z of n is this time an input to the autoregressive part. And the autoregressive part, I always start from the output, which is y of n, because I need y of n minus 1 and y of n minus 2, y of n minus 3, up to y of n minus capital N. How am I going to do that? I will achieve them by having delays. A lot of delays. And the last delay will be multiplied by, is there anyone who can tell me what is the scale when k is equal to capital N, the last one? So look at this part. When k is equal to n, when it reaches to n, it corresponds to y of n minus capital N, and it is multiplied by something. What is it? A sub n, a sub capital N. That's almost correct, but notice that we have a minus sign here. So essentially we will have minus a sub n. You remember that we were always multiplying with minus a for the feedback loop. And then it is added to what? It is added to y of n minus capital N plus 1, the previous one. And that previous one is actually minus a sub n minus 1, capital N minus 1. So the last layer, the bottom layer, is going in the reverse direction by multiplying with minus an, and the one before that is minus an minus 1. And it goes up all the way. For example, at this point, it will be minus a2, because here I will have this way corresponding to minus a1. And finally, the input will be combined, and everything inside the parentheses is achieved at this point. And that everything is multiplied by 1 over a0. And that would make y of n. I feel that even this much is complicated enough, right? But from top to bottom, we have b0 and 1 over a0, then b1 minus a1, b2 minus a2, etc. at the same layers of these two shapes. Can you guess how I'm going to minimize this? By interchanging the autoregressive and moving average parts. The right-hand side long thing will be the first, and the left-hand side long thing will come later. So I'll interchange their places, the right-hand side and the left-hand side. And I'm going to cheat at this point, because I have this lasso tool, which I hope I can copy. But I don't know how to do that, because it's just moving. Is it possible to have a yes, copy, good. And then I want to paste, but I don't know how to paste. I copied, but I couldn't paste. Come on. I was trying to cheat, but I couldn't, so I will have to draw it. So I will draw the right-hand side now, and I will try. The right-hand side has an output which is having delays, then going to the left, and then another delay, and going to the left, and then going to the left, and the delay, and the last going to the left. Going to the left was, the last one was minus AN. I'm combining it with minus AN minus 1, but that's, and combining it to minus A2, combining it to minus A1, and combining it to the input, and putting a 1 over A0 here. So I was able to draw. Now, this shape and this shape are the same, okay? I just copied from there. Now, I will copy the left-hand side shape, which is the input is delayed, then delayed, then to the right and delayed, and to the right. To the right, it was, the last one was Bn, and the one before that was Bn minus 1. This is B2 combined with this one, which is B1. And at the top, it is combined with B0. And this is the output. And I am claiming that if the input of the system is x of n, then the output will be y of n. So I just swapped their places. Then what am I going to do? Then I will merge these middle branch signals using only a single delay element every time I have a pair of delay elements, because if the top signal is red and red here, then this green and this green are the same. And then this blue and this blue are the same. And then this, finally, this black and this black are the same. And let me put a yellow tag. This yellow and this yellow tagged points are the same as their counterparts. So I will merge the in-between, just merge them and make it like this. With a scale of 1 over A0, and then I will have a single delay element. And that will bring me to the green point. So from the green point to the left and to the right, I can proceed. And then another delay element, which will give me the blue point to the left and to the right. I can split from there, etc. Then I split to the left and to the right and have the last delay, and its output can go to the left and to the right. To the left, it will be minus A1, minus A2, blah, blah, all the way down to minus AN minus 1, and finally minus AN, and I will collect them. Oh, that's incorrect, because there are other things in between that I have to collect, like this. And at the right-hand side, I'll do, again, similar things. The right-hand side branch will continue with Bn, scaling of Bn The one before that is bn minus 1, and I collect them. I continue my collection. This one is b2. This one is b1. And finally, all the way up here, where the top one is b0. So this is the input x of n, this is the output y of n, and this is the minimal representation that I ask from you to have for any given differential equation. So a question here, the delay element makes xn to xn minus 1, then how do we get yn minus 1? This is the only thing that I don't understand. It's neither xn nor yn that we are delaying here at this point. Okay, the signal is a different signal. It's neither x of n nor y of n. It's just that signal over there. And what, let's give the signal, the red signal, the two red dots over there, you see? The red signal. Let's give a name to it. Let's say z of n or w of n. Oh, I don't care. And I am now delaying it to come up with the green points, which are the same because they are both delayed versions of the green, the red signal. So the green signals are the same. The right-hand side green signal is the delayed version of the red signal, and the left-hand side green signal is also a delayed version of the red signal, the same red signal. So the two green signals are the same. And then we delay them further to go obtain this time the blue signals. So the blue signals are the same. So why do we have two separate blue signals or two separate green or red signals? Instead of that, I'm just merging them with a single delay element at the right-hand side shape. And that's what I do. Maybe I should put some labels. This is the red signal now. This is the green signal. This is the blue signal. This is the black signal. And this is the yellow signal that we have. So these two shapes are the same now. That's what I'm claiming. And in the previous or the left-hand side implementation, I was using how many delay elements? I was using n times d delay or n times delay elements. N delay elements. Oh, sorry, 2n delay elements. Because n delay elements at the right-hand side, n delay elements at the left-hand side, and they are just too many, 2n delay elements, whereas here I have only n delay elements. I am sharing the delay elements, in other words, both utilizing for the autoregressive and the moving average part all at once. But I cannot do it, I cannot do the sharing with this implementation. I cannot do that. How can I share it? One of them is, as your friend has asked, one of them is delaying the output y of n. The other one is delaying x of n. I cannot share them. They are very far away from each other and there's nothing to share. Their corresponding signals are different. Their inputs, the inputs of the delays for this shape at the right-hand side and the left-hand side, they are different signals. How can I share them? I cannot in this way. So I have to just flip around their orders. First, I apply the autoregressive and the moving average, and it's still the same system because of the property of LTI systems. You can always interchange LTI modules. You can do one first and then the other one next. Okay? So when I do that, now I have a different layout. And I can see that the delay elements now correspond to the same inputs. Therefore, their outputs are the same. And that input is neither, the inputs of the delay at the first stage is neither x of n nor y of n. It's different. It is something in between. It's a different implementation. But now they can be shared because this, for instance, I can say uh, z of n, and then here I have z of n minus 1 at this stage and z of n minus 2 at this stage, blah, blah, all the way down to z of n minus capital N at the very bottom. So they are the same signals. So I merge them, okay? I hope it makes it clearer now. And I'm somehow worried that, of course, it's not very clear. I mean, there are some problems. You may understand right now, but when I give a question to you, it may be difficult. So I strongly suggest that you have to study from the book with the related chapter, okay, of Oppenheim's book. This implementation is important, and you have to study. And it's getting way and way more difficult if the length of the right-hand branch and the length of the left-hand branch are different. If one of them is taller than the other one, how will you merge them? They will not exactly match. Okay, and that's a difficult situation. But I'm giving you a cheat here. I'm telling you that I'm going to ask it. I will say that, for example, the length of the delay elements for here will be m, and the delay of this portion will be n. And I can ask a question for m greater than n or n greater than m. Here, n is equal to m, so they have the same size, and they are easily interchangeable. And the sharing of the delay elements is very much possible. They just match perfectly. Instead of 2n, now we have n delay elements. How about the other case? When n is greater than m or m is greater than n. And I'm telling you that I'm going to ask this as an exam question in your midterm. So if you are a proper electrical engineering student, I would take it very seriously, and I would literally solve these cases for 3x2 or 2x3 cases, for instance. And let me tell you the result. The minimal representation must contain the maximum of m and n. For example, if one size is 3 and the other size is 2, normally it requires 5 delay elements. But with the minimal representation, it must have 3 delay elements. Whichever is larger, m or n, you have to have that many delay elements, no more than that. So it's not 3 plus 2, which is 5 delay elements, but only 3 delay elements. If it is 3 and 3, you will again have 3 delay elements. If it is 3 and 4, this time you will have 4 delay elements in the minimum representation, Is the question clear? The answer may not be very clear, and it's impossible to proceed, but you have to at least understand the question. So there is a comment here. Using 2 delay element common and adding 1 extra delay element to the greater side than adding to the main delay elements, maybe. Yes, exactly. But see, the problem is sometimes I will erase these because it's complicating things, but the situation may be like this. The input maybe will not come. Let me go over this one. The input, which is shorter one, may not come from here, but it may come from here, and we may have nothing here. Okay, if it is shorter, or if the left-hand side is shorter, or maybe you just don't have this part and this size is shorter. So is the shortness from there to there or from there to there? Or similarly, will it be short like this where y of n is as you see, or will it be like y of n will be actually here and you will have nothing here? So it will be short like this. Which way? It's not as simple as you suggest. That you, in general, what you suggest is correct, but adding to the main delay element, where's that main delay element? Is it to the top or to the bottom? So is the output from here or from here? Or is the input from here as expected, or maybe from here, if it is one short, if the size of it is one short? I think I'm confusing you because I want to, because I want you to literally do it. Without doing it, uh, just couldn't undo, so I'm just erasing very carefully. Okay, I did it. You have to exercise on it. Please do so. Please. Please solve some examples. Now, it's time to give some break. But we made a very, very long, with any standards, even with the in-class standards, this was a long lecture. You may be tired of this one. And I think I wouldn't go into the second part, which is the implementation of continuous time, linear and time invariant LTI systems, where we are going to use differentiators converted to integrators. And its complexity is even more than this one, because the difference equations directly reflect to delay elements. It's simple, but the differential equations contain derivatives. However, we are going to implement with integrators, the dual operators. So that would be even more complicated. I think if we do half an hour more or something like that after a break, that wouldn't help. So I believe that we must stop at this point. We will meet again on Monday, and on Monday we will make a fresh start to continuous time LTI block diagrams. But in order to understand it better, I suggest that you go and find the related video from the previous year's lectures. Okay, go and find them, watch them, and then go to the Oppenheim's book, read it again, and then maybe watch it again. And afterwards come to the class, and only then you will have a deep understanding of the situation, and you will be able to solve questions. Otherwise, I find this one particularly difficult. The difficulty is very technical. It's not ideally difficult, but it's very cumbersome, and you get, or I get, easily confused about which one comes where, etc. So it's difficult for me, and therefore I find it difficult to explain. And you may find it difficult to understand, therefore. So please make a pre-study. Okay, find the videos related to this one, related to this one, and the continuous time implementations using integrators. Please do that. Please watch them. Please read the chapters before coming to the class on Monday. You have some time before that. Okay? So thank you for arriving to the class on this kind of holiday. If you have any other questions, you may ask. But I suggest that you have to go through it again and again and again, and that will give you some understanding, I suppose. Okay, so, all right, thanks then. I will stop the recording, and then we will meet next Monday. Take care. Bye-bye.